Today we're going to start section 3.5. In 3.2 we started with addition, and then subtraction is 3.3. Multiplication was in 3.4, and now we're looking at division of whole numbers. So just like we started all three of the other four sections, we're going to start with the definition for division. For any whole numbers a and b, where b is not 0, a divided by b equals c, if and only if c is the unique whole number, such that b times c is equal to a. A is called the dividend, b is called the divisor, and c is called the quotient. So from a very concrete perspective, it's something like this. The reason that 10 divided by 2 is equal to 5, right? That's this description, is because 2 times 5 is equal to 10. So it's the number that we need to multiply 2 by to get back to 10. Yep.
I have a question. So it might be kind of stupid, but do you always put the bigger number at the front? Like you divide that first?
So I want to be a little bit careful about how I answer you because we're working with whole numbers right now, so the answer is yes. But that's not true as a general statement, right? Like you can do 2 divided by 5. It won't equal, 2 divided by 10. It won't equal 5.
Yeah.
But there's nothing wrong with the smaller number being in front of it. But right now we're only working in whole numbers.
Okay.
So as you see things at a younger grade level, yes, you'll always see the larger number written first.
Okay.
All right, so what we're going to do is we're going to see, I think it's four different models. Yeah, 4 different models for division. So we've done this modeling perspective before. This is not the first time. The first one we're going to look at is the repeated subtraction model. So here's an example of a problem where a repeated subtraction model is sort of the perspective of this division problem. Junie has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So if we're working with young children, what they're probably really going to do is not divide, right? She's going to have her 6 friends sitting in front of her, and she's going to say, you get a rock, and you get a rock, and you get a rock, all the time until she gets to group them, friend number 6. And then she's going to repeat the process. Okay, does that make sense? That's why this is a repeated subtraction problem, is because she's repeatedly taking away. And because there's 6, every time she hands them out, she's repeatedly taking away 6. So the perspective that we're looking at here is repeatedly subtracting, in this case, 6, because she's handing out 6 rocks at a time from the 24. So that would give me 18. I would take away 6 again to give me a 12. I've run out of space, so I'll move over. 6 again to give me 6. 6 again to give me 0. And if we count the number of 6s that we repeatedly subtract, that's how many rocks each friend got. So we have something and we are repeatedly removing it from the inventory. So it doesn't mean that I have to solve this by repeatedly subtracting, like I just showed you, but that is the thinking behind what the child is doing as she asks herself this question: how many rocks will the friends get at the end? And it does end up being, of course, a division problem. It's really 24 divided by 6, and I get 4. Okay? So that's one of our models, repeated subtraction. And we will see a algorithm that has this at play a little bit in it. Doesn't work out exactly like this. I don't just completely subtract the same number every time, but there is a variation to it that keeps it similar. There's 2 set models. There's a set partition model that we're going to call, and then I've got a variation to it. And the reason I have the variation is because it actually shows up when you look at things in chapter 7 when we get to prop and stat, which some of you have already taken. So I want to show you that there are 2 set model perspectives. So we'll use the one that they've got first. So we've got Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So if we think about it from this perspective, what she can actually do is she can actually make 6 groups. So there's groups. So we're doing these sort of 6, groupings here, kind of like our groups of friends. So this one looks more like a visual imagery of what's going on. And then we do the same thing that we did before, right? We give them their rocks. So, whoops, let me do this. So we have 1, 2, 3, 4. Well, I needed 6 groups. Sorry, I didn't get enough groups in there. Okay, I realize the groups are overlapping. They're not really supposed to. Let's see if I can shift that enough. All right, we'll go with that. There's 4, 5, 6. And then we go through all the friends again. We group them up. We have 1, 2, 3, 4, 5. Wow, 5, 6. This is not large enough to hold my rocks. That might work better. I'm going to change my color of my rocks. Maybe that'll help. Then we have 6 rocks. We have another 6 rocks. So far we haven't given them all away. And then we have 1 more. Oh, I did give them all away at 4, didn't I? 6 groups. Oh my goodness, I'm already thinking about my next model. Okay, I think that's all of them then. There we go. So we're thinking about putting them in groups instead of repeatedly subtracting them. So we're more thinking about what I have in my hands as I receive them than I am about, from the perspective of, what was her name? Junie, of what I've released from my hands as I handed them away. Okay? Notice the word problem didn't change. It's the perspective that we're looking at that's different. The other one is actually a slightly different question. Junie has 24 rocks, and she bags them together in groups of 6. So this time, I'm going to have 6 rocks in a bag. So if you can imagine taking my bag and making 1, 2, 3, 4, 5, 6, and then there's 1 bag of rocks. Right? And then I have 1, 2, 3, 4, 5, 6, and here's another bag of rocks. And then I have 1, 2, 3, 4, 5, 6, and here's another bag of rocks. And then the last one would be 6, and I have, oops. Okay, last bag of rocks. So this one's a little bit different. She's still removing 6 at a time, but as she's removing those 6 at a time, she's not handing them to the 6 friends, she's making piles of 6 rocks. So on this perspective, I would have never answered the question over here. Each of the friends got 4 rocks, right? Over here, while I'm still doing 24 divided by 6, and I'm getting 4, this time the rocks are being grouped into 6 instead of the friends, right? I mean, I'll have 6 friends, well, maybe I do, but they don't all get the rocks, right? I have 24 rocks, I've put them in groups of 6, and I end up with 4 friends getting my rocks. So my grouping feels a little bit different. So we can either group things so that I figure out how many things I want in each group. That's actually the one I just switched from. I want 6 things in the group. And what that does is that then determines how many groups I have. Or I can consider, well, how many groups do I want? And then that will determine how many items are in each group. So let me give you a classroom example of something that I think about on a regular basis. I oscillate between wanting to have groups of 2 when I have you guys work in pairs. I prefer groups of 2. The reason I prefer groups of 2 is because I think that sometimes when there's groups of 3, somebody just sits there and doesn't say anything. And I want everybody to be engaged. So I like groups of 2. But here's the problem. If I have groups of 2, I have more groups. And there's only one of me. Which means that if I have this class, and we have 14 people here today, I'll have 7 groups. So if you're in 7 groups, I potentially may be pulled in multiple directions at the same time because there's only one of me and there's 7 groups. But if I make the groups a little bit bigger, I have fewer groups that I have to be moving between, right? So if you're in groups of 3 today, one of you will have a group of 2 by doing so. But if we put you in groups of 3 today, you would end up only having 5 groups. So I would potentially only have to have 5 groups of people to answer questions for, right? So you give or you take. You can't determine both at the same time. I have to choose which one's more important on a task at hand. And I vary, it depends. My group of 30, they cannot be in groups of 2. That's not an option. There's too many of them. So, yeah, that's something that we do, right? We decide the size of the group, or we can decide the number of the groups, but we can't determine both independently. They affect one another. The last one is a missing factor model. And again, it's the same word problem. The word problem is that Junie has the 24 rocks. She wants to give them again back to her 6 friends. I know I made a variation on the last example, but we're back to the 6 friends. And the question is, how many rocks will each friend get? So when we're thinking about the missing factor model, we're thinking more like about this definition we had up here of division, all right? So we're thinking about, what do I do when I have 24 and I'm dividing it by something and I need to get 6 friends? What's the missing factor? What number needs to go in that blank? Or equivalently, if you want to think of it like this, you can. 24 divided by 6, and it's going to equal what number? These are two descriptions of the same thing. I'll put a blank there. So we rewrite it, or we rethink about it as multiplication instead, right? And the definition of division said I'm supposed to multiply these 2 values in order to make this work. So instead the question becomes 6 times what is equal to 24? Or what times 6 is equal to 24, depending on which one I've thought through. And the answer then, of course, would be 4. And so they each get 4 rocks, because 6 times 4 is 24. So you're thinking about it in this one more from an equation perspective instead of from a picture kind of perspective. Okay? So I'd like for you to shift and to get into those groups of 3 that we just talked about, although one group is missing one person. And what you're going to do is you're going to actually create one word problem, and you're going to solve it in the different methods, okay, with the exception of the set variation one. That one has to be different. The way it words it is a little bit different. Yeah, the second one, the C, one that says C. So like it says, 3 of the 4 models above do not represent different types of word problems, like they did with subtraction, for example, but rather represent different ways of solving the same word problem. So you're going to create a word problem, and you're going to solve them with each of the 4 models of division. Note, 3 of the 4 problems will be the same, A, B, and D. Okay? So you only have to create 2 examples, but this time you're going to solve them, whereas the other times when I asked you to create examples, you weren't solving them. Okay, so go ahead and shift, find your people, and take a look at that one, and then we'll come back and see what you guys came up with. Okay, so what we're going to do on this is we're just going to hear the word problems that you created. So one of the things that I hope that this helps you to think through is that there are some times on this test particularly, or other tests, where I have you create things that are your own too, right? Like you're creating something that you would use in a classroom or on some kind of an oral test maybe, or something to talk with the child about. And so I want you to be able to come up with an example that's child appropriate, or age appropriate to a certain age, and that it's unique, that would fit maybe that child or that context or something too. But usually something that's your own, not something that you've just recycled from somebody else or whatever. So hopefully as you hear some different ideas, it'll help you to be thinking about some of your others. So each group's just going to let us know, and you can choose one of the 2. It doesn't matter to me which of the 2 problems you created. They probably are very similar. But so we'll just start over here with this group with Candace and y'all. So would one of you tell us what word problem you created? Wonderful. And what kid doesn't like donuts, right? Absolutely. 12 donuts, and we're dividing them up. What do you guys have in the middle?
We have Dr. McWilliams says 36 frogs with 6 students in his class. How many frogs does each student get?
A lot of frogs. Maybe too many frogs, right? Yes. 36 frogs, and we've got 6 students in the class. All right, my group of 2 right here. Karis or Jenna, who wants to talk?
Okay. I'll give the other one. Okay, so we said Carlos has 12 pieces of gum. He bags them in groups of 4. How many of his friends go back?
Awesome. So that's an example of the part C one. So we've determined how many are in each group and then how many people get the groups themselves. Sure. Okay, back corner.
It was the same thing, just our numbers were switched. So
Okay.
It was 20 pieces and 4 pieces in each bag.
Okay, so far we're 3 for 4 on creating word problems with food. Just saying. We're not eating the frogs. Sorry, ladies. Okay, last group over here. Yes. What do we have?
He said, if Gracie has 10 pieces
All right, so everybody wants to do things with food, all about food. It's Halloween, right? That's why we want to do candy? Cool. All right, so you have the right idea, yeah? So we're dividing up objects of things into groups or among groups of people and seeing what we end up getting. Notice most of the ones that we've done, in fact, all the ones that you guys did and the ones that I gave, evenly divide. You could have examples where they didn't, depending on the curriculum that you're working with at the time, right? So if you're working on things that would have remainders or division algorithms where there's remainders present, it's perfectly acceptable that you would have a problem like that. I can't remember if your book does any of those at this particular point in the section or not, but if they do, just let me know. That's okay. I mean, you can have a remainder. You know, there's 2 pieces left over or something like that. All right, so we're going to do one more thing today. We're going to take a look at some properties, the whole number properties, and see whether or not they relate to division. So we did this for addition, we did it for subtraction, we did it for multiplication, and now we're going to look at it for division. Okay, closure. It's your favorite property. Closure means if I take 2 numbers, in this case in the whole numbers, and I divide them, because my operation now is division, do I get another whole number? No, at least I don't have to, right? Jenna, can you give me an example?
2 divided by 10.
Fabulous. 2 divided by 10. We saw that one earlier, right? This is not an element of the whole numbers. I get a fraction, yeah? So there's no closure property. Closure does not work for division. How about commutative? No. Why not?
10 divided by 2 is not equal to 2 divided by 10.
Right. We're going to stick with the 10s and 2s. 10 divided by 2 does not equal 2 divided by 10. You bet. The order matters, right? Which is why Emily was asking the question. I don't know where you went to. There you are. Why you were asking the question, which was the order, right? Because it matters. It changes the value. So there's no commutative property for division. Now, you might not be able to answer this one quite as quickly. Associative. Your gut tells you the answer is no. So as we do an example that we're going to create, we're going to try to do an example that keeps things in whole numbers. So the answer is no. So let me show you an example. If I was showing you an example that this doesn't work, I'd like to have numbers actually stay whole as I work with them. So for example, 6 divided by, actually let's make it bigger, let's do 12. 12 divided by 2, hang on, I don't need my numbers. I want to keep my numbers right. 4. 12 divided by 4, and then divided by 2. That'll work. And then we're going to compare that to 12 and then divided by 4 divided by 2. Okay, so we have the same numbers in the same order, 12, 4, 2. But the parentheses group the first 2 on the left and they group the second 2 on the right. Order of operations on the left, we're going to do 12 divided by 4. So 12 divided by 4 is 3. So the left side is 3 divided by 2. On the right side, I have 12 divided by, and what's 4 divided by 2? 2. 12 divided by 2 on the right-hand side is 6, and that is definitely not equal to 3 divided by 2, which is actually 3/2. It's fractional at that point, but yeah. So there's no associative property. What do you think about identity?
Yeah, 1.
Almost.
Oh.
So identity has this sort of annoying feature that it has to work 2-directionally, right? So I'll use my 10 that you guys had before. 10 divided by 1 is definitely 10. So like that, it works. It's almost like it's a half identity, right? It works if you divide by it. But if you switch the order around, it doesn't work. So this happened with subtraction. Do you remember it? 0. Sort of had this half identity. If I subtract 0 away from things, it works. But if I do 0 minus something else, it doesn't work. So there is no identity element for division. We had a property with multiplication called multiplying property or the multiplication property by 0. So we're going to look if there's a division property by 0. In other words, if I do 0 divided by 10, I get 0. So that's like a half division property by 0. Like that's part of it. But I run into a problem over here if I try this one. What is 10 divided by 0? It's undefined. And in fact, this is a really good place for us to talk about why that word undefined comes about. So I'm going to flip back to the very first slide we had that talked about division and its like definition. Okay? Undefined. I wonder why y'all are looking at there. How about that? Undefined. Is that better? Okay, so our original definition for division, I don't know if it had these letters in this order, but it said something like this. A divided by B equals C. If I can take these two, multiply them, B times C equals A, right? That's what the definition of division is. So if I tried that with my 0, 10 divided by 0 equals, and let's actually say it equals something, we'll call it C as well. What would have to be true is that I'd have to be able to multiply 0 times C and get back to 10. You can't do that. And that's why division by 0 is undefined, is because the definition for division excludes it. There's no way I can multiply 0 by something and get back to 10 or anything else, right? I can't. So there is no 0 division, so there's no division property by 0 either. The last one's distribution. Again, this one takes a little bit more work like the associative property does, but your gut tells you the answer is no, everything else has failed, so why not this one, right? So let's actually see an example of one. So it kind of half works as well. Let me show you. So if I do 20 plus 10 divided by 5, and then to do distribution would mean that I would do 20 divided by 5 plus 10 divided by 5. That's what it would look like. So let's check out this direction of this. So 20 plus 10 is 30. And what is 30 divided by 5? 6. 20 divided by 5 is 10 divided by 5 is 2. And 4 plus 2 is 6. So it works in this direction. It did. The failure comes in the other direction. So let me show you that one. So this is the one where it works. So let's do this one. So I have to be able to distribute the division, just like with multiplication, from both directions. Through here like I did here, or through here like I did here. So as I'm trying to think through the distribution, they look like this. Sure, we'll use green. And now I'm trying to go like this, okay? So if I do this, I'm looking to see whether or not, still need more space. I can do 20 divided by 10 plus 20 divided by 5. Okay, so let's start on the left. The parentheses is the 10 plus 5. So I have 20 divided by what on the left? 15. 20 divided by 15 is not a whole number. Now, that's okay, because we know that whole numbers are not closed under division. But the problem on the right-hand side is that we do get a whole number. 20 divided by 10 is 2, and 20 divided by 5 is 4. So on the right-hand side, I do get a whole number 6, and whatever is happening on the left-hand side, it's not inside the whole number system any longer. In particular, it's 20/15ths, like so, which would reduce to 4/3. So 4/3 is not the same as 4. So it fails to be sort of two-directional, just like the identity failed two-directional and the 0 property failed to be two-directional. We have a lot of problems, and it's all hinging back on the fact that it's not commutative. That's really what it's hinging back on. So we're going to stop right there for today, and we will pick up and finish with division algorithms when we start back again on Monday.